All right, maybe here's the simplest example. The force acting on that mass attached to spring is directly proportional to its displacement in this way, where the direct proportionality is just 1, so it's just going to be just F equals negative y. And the differential equation, a theory from differential equations say y is going to be in this motion in sine t. So that's the answer. That's the principle. And here's the mathematical answer. Surprising, there's this only one possibility to that. That's the one part. And another part is involved in here is the right triangle, and this principle is explained using this mathematics from the right triangle. So in this part here, I'm going to review a little bit about the things about the sine t. Although I said it is right triangle, this only makes sense when t is in between 0 and pi over 2 seconds, but we quickly switch to the radian. But for bigger numbers, or even to the negative numbers, we have to extend our definition from right triangle to the circle. So here's the unit circle. All right, here's my unit circle. Here's the radius 1, and it doesn't look like a perfect circle. So I write down x squared plus y squared equals 1. That indicates that it doesn't look like a unit circle, but this Cartesian equation explains that, and this is supposed to be a perfect unit circle. So here we have t seconds. Remember, we're looking at this thing in this physical motion, so our t is the magnitude of this time, t seconds. And here we interpret it as, using the same magnitude, we turn it into t radian. So we turn this one into an angle. So here's an angle, for example, like that. So that's our t radian right there, t radian. Then we're interested in the sine t. What is the sine t involved in here? That the circle definition of a trigonometry, and you look at this terminal side and look at the terminal point right there, and here is the definition of a sine t radian. Let me just abbreviate it like this. That's the way usually we do. And is y divided by the radius, which is 1. So in the case of the unit circle, you know the y-coordinate is the value of the sine in here. So what is the y-coordinate here is exactly this distance right there, this vertical distance. But that looks like exactly the orientation of representation of this number is the same as the displacement, the vertical displacement of the mass attached to the spring. So that's the y value here represented vertically, and there was a spring mass system over there. So I'm going to put this one side by side, and even with the graph of a sine t, and to see this amazing connections all together. So I brought up this mathematical demonstration here. So this is the circle, and right now we have this terminal side right there. I'm going to go ahead and change the cursor. All right, we're back. So that's the 0 angle right now, and that's the terminal point, and the y-coordinate there is exactly the sine value at the 0 value right there, and this is a unit circle. So this is the equilibrium position of the mass attached to spring, and this is the beginning of the graph of a sine, and this is time expansion. That right now, and this is supposed to be 0 seconds, the separate system in here, although it is extended to a same x-axis. Consider this one as t equals 0, and this is roughly interval from here to there is roughly 2 pi. So here's a picture. So this is supposed to be t radian. Right now this reads 0.6373 radian. For the spring mass system, it's 0.6373 seconds later, and the mass is in this position, and we know from this picture it's actually heading up. And the circle, the terminal point is over here, and its y-coordinate is exactly the same value. So this height is the sine value. That's the sine t in the circle equation. And according to that mathematical connection I showed it earlier, the position is exactly the sine t. That's the differential equation result. And we're sketching here an average. This is not a straight line. You can see it's kind of slightly curved. And here after t seconds, and this is expansion of t, and here's represented as an angle, and here's t seconds, and we plotted the location, displacement of this mass in here. So if I move a little bit further, and you can see that exactly translates this height and displacement and y-coordinate of the graph of this function and all together. So another way, this t is increasing in here. It's kind of funny to say that the time is increasing in constant speed. Quite confusing notion, but t is increasing over this horizontal axis with a constant speed. That translates to this one rotates around the circle with a constant angular speed, and this creates this shadow on the wall, and slightly different. It's not a constant motion you can see as we play the movie, but that's the connection. The Hooke's law, the principle of a harmonic motion, started from here, and the mathematical answer through the differential equation says it actually the shadow of this circular motion with constant angular speed, and that is sketched over here like this. So let me play the movie. So as you can see, the circle around with a constant angular speed, and what this shadow to the wall creates this motion, as you can see, that passes through this equilibrium position a little bit faster than the speed of other positions, and when we reaches the position 1 here, kind of slows down and have a very small magnitude of a speed. It's definitely not constant velocity speed movement. It's a shadow from this constant angular speed, and that is the mathematical the secret is revealed through this calculation and differential equation. So once you figured it out, that motion of the graph, and it's revealed in this way in here. I realize it is not showing everything, so I made it a little bit so you can see how the last bit of sine graph looked like.